Hello everyone, this is Dhanlakshmi, Assistant Professor of Triply Department from RMD Engineering College. So in this session, I would like to discuss about phase control rectifier, which is our unit 2 of power electronics. We might be very familiar with rectifier. So now we'll go for phase controlled rectifier. So when we say phase controlled, obviously the devices earlier in the earlier classes we were learning about rectifiers where simply the diodes will be placed in the configuration in the circuit diagram, and where, as we know, it's a rectifier which will convert AC to DC. But when we say DC, the output side, the output will not be in the form of pure DC. We will get it in the form of unidirectional quantity. Later on, that can be fed to filter, LC filter, then it can be made as more DC or stiff DC. But here we are going to discuss about phase controlled rectifier, which means that here the devices or the controlling or switches, what we are going to use is a thyristor. Using with the help of a delay angle or firing angle or of the gate control, we are able to control the rectifier. So we will discuss about this. So here is the circuit diagram for a single phase full bridge converter. So in the single phase full bridge converter, here you can see. Okay. So here you can see that it's a single phase full bridge converter, where the load connected here is RLE load. And as we know that in a single phase full bridge converter, we will be having two legs and four switches, T1, T2, T3, T4. So here the input side is our AC source. So here we can see that our input is AC, and where at the output, at the load side, we have to get the DC, unidirectional quantity. So here the working of this circuit diagram, we all know about it, but anyway, just to recollect, let me discuss the same thing. So here during positive half cycle, so we can see here that it is in the configuration of bridge. During the positive half cycle, here this will be positive. During positive cycles, thyristors T1 and T2 will be conducting. So thyristors T1 and T2 will be conducting. Why? Because they both are forward biased, and the remaining thyristors T3, T4 are reverse biased. Right? So therefore, the flow of current will be from the source. So the flow of current will be from the source to the thyristor T1, then to the load, and back to T2, then back to the supply. So this is how the current flow will be from T1 to T2 during positive half cycle. So here we can note down that the current flows in the load from positive. This is this way, from positive to negative, right? Whereas during the negative half cycle, you can see that the thyristors T3 and T4 will be conducting, because during negative half cycle, here the polarity will be negative and here the polarity will be positive. So therefore here you can see that now the thyristors T3 and T4 will be forward bias. T3 and T4 are ready for conduction, that is they are forward bias, and after giving, once the gate is triggered, they will conduct it, right? They will conduct after a delay, which is given by the delay angle. Right now, the flow of current will be from positive of the supply to the thyristor T3, and again back to the load, and then through T4 and return to the supply. So here also, when you see that during negative half cycle also, the current flows from R to B, that is it flows from this direction. The current flows in this direction. So here you can see that in both positive cycle as well as in the negative cycle, the current flows in the same direction at the load end. So thus you can get the unidirectional quantities. So here we can see that in the that the current flows in the positive cycle through thyristors T1 and T2, and the current flows in the negative cycle through T3 and T4. This is the thing. We'll go for the next slide. So here we can clearly see that during positive half cycle, the current flows from the source to T1, the load, and back to T2. Right? And in the negative half cycle, again the current flows from, you can see that during the negative half cycle, the polarity has been reversed here at the source. So therefore, you can see here it is negative and here it is positive. Once again, let me take that. Therefore, here you can see that during positive half cycle, here it is positive and here it is negative. So this is for positive half cycle. And during the negative half cycle, the polarity has been reversed. So here it is positive and here it is negative. So therefore, now the thyristors, so during the positive half cycle, the thyristors T1 as well as T2 are ready for conduction because they both are forward biased. And whereas the thyristor T3 and T4 are reverse biased, because here you can see that positive to anode of the thyristor make the thyristor to forward bias. Similarly, positive to and then you can see that positive to cathode of the thyristor will make the thyristor to be reverse bias. So T3 and T4 are reverse bias and T1 and T2 are forward bias. So therefore you can see that the current flow will be from the source to the thyristor T1, then to the load and then back to thyristor T2. So now you can see the current is flowing in this direction. That is this direction, let me assume it to be positive direction. Whereas during the negative half cycle, when the negative half cycle of the supply comes, right? When the negative half cycle of the supply comes, here you can see that the polarity has been reversed. So here you can see that the polarity here is negative, whereas the polarity here is positive. So therefore, the current now flows from again during negative half cycle, the thyristors T3 and T4 are ready for the conduction, whereas thyristors T1 and T2 are reverse bias. So now the current flows from the supply, from the positive, that is from this terminal of the supply to thyristor T3, then back again flows to the load, then it goes to the thyristor T4 and back to the supply. And now also during the negative half cycle also, if you see that the current flows in this direction from top to bottom, which means that now the negative cycle is also being rectified. Right, so this is the idea of connecting, or this idea of how this works and how this works in both positive cycle as well as in the negative cycle. You can see that all the negative cycles have been rectified here. So all the positive cycles will be directly connected, and here the negative cycles have been rectified. So here you can see the waveform of single phase full converter. When we set alpha to be less than 90 degree, it will work in the rectification mode, where you can see that. And here you can see that the output voltage is following. The output voltage is what we are getting is the just follow up of the input voltage. And here we can see that this extinction portion, right? This extinction portion we are getting because of this, because of the inductor in the load. Right, when we have the inductor, when my load is going to be L load, when I have inductor in the load, this inductor will be storing energy in one cycle that has to be extinguished in the next immediate cycle. So therefore, here you can see that the energy stored in this, the extinguishing of the energy is taking place during this period. So this extinguishing portion or extinction part will come whenever we have the inductor load. Right. So this is how you can see that it is just following during positive cycle, thyristors T1 and T2 are conducting, and this extinction will be there because of the inductor. And here you can see that in the next half cycle, thyristors T3 and T4 are conducting. Right. See, for alpha, when alpha goes above 90 degree, right? So this is what happens here. When you make your firing angle alpha to be greater than 90 degree, now this converter will be acting as will be working or operating in inversion mode, which means that now the power is flowing from load to source, right? Usually here we can see that in a converter, in rectifier, the power flows from, you can see that in the power flows from source to load, right? That is, the power is in the positive direction, which means that the source is feeding the load. And whereas in case of when we make alpha to be greater than 90 degrees, and when the E polarity has been reversed here, the EMF polarity is reversed here. Now this is capable of delivering power to source, right? That is, you can see that the power is now flowing from. So this is what I'm trying to say. Here you can see that now the power that is during alpha greater than 90 degrees. When we set alpha greater than 90 degrees, this will be operating as an inverter, line commutator inverter, which means that now the load is going to feed the power back to source. Now the load is going to feed the power back to source. For this, your EMF, the polarity of the EMF should also be reversed. So the right, so this EMF, this E should be reversed in order to work in a inversion mode. So that is the power is negative here, because here you can see that in the voltage waveform, this voltage, you can see that voltage becomes negative when we make alpha to be alpha greater than 90 degrees. So when alpha is greater than 90 degree, the voltage is negative, so the power is negative, because the current will be in same direction, and the current will be positive in both rectification as well as in inversion mode. Whereas the voltage alone will be reversed here. So because of this reversal of voltage, that is during the negative, because of this negative voltage, the power is also negative, which means that now the power is flowing from the load to source. Here we can see that you can find the difference between alpha less than 90 and alpha greater than 90 degree. So when alpha is less than 90 degree, this will be acting in rectification mode, where the power is fed from AC source to load. Whereas when you make alpha greater than 90 degree, this will be working in inversion mode, where the power is fed from load to source. Right? So this is the idea.